Morning, everyone. Hope you're doing well. As you can see, I'm in Italy here. Might as well take the opportunity to do some traveling since we're teaching remotely. Anyway, hope you had a nice weekend. Yeah, we're moving along here. I should say we're moving a little slower than normal, but that's okay. You know, hey, it's still a remote class. We're doing these questions, which are something I don't usually do, but since it's remote, I'm trying to help you out. So that's slowed down the lectures a little bit. But what that means is that we will probably delay our first exam probably to week 5 or so. Are we in week 3 now? I can't figure it out. I'm always very confused because we started on a Thursday, but hopefully we will figure it out. But don't worry, we will certainly have plenty of warning and plenty of information before the test. I just wanted to give you a general sense. You know, this is a situation where you'll have a span of days to actually take the exam. So there should be, you know, no problem with the scheduling and all that, since there'll be so much flexibility. Okay, before we get started on today's material, let's see if there's any questions in general. All right, good morning, thank you. Yes, it's week 3. Yes, week 3, thank you. Hansa, it would be great if you emailed me so we could set up a meeting. I can't meet right after class, but I would be happy to set up a meeting anytime you'd like. Or we could do it through email, okay? Can't meet right after class. All right, great, thank you, Hansa. All right, let's go ahead then. We are talking about some pretty cool stuff, if you ask me, but you know, I'm a big nerd, as you know. We are talking about theories of perception, of course, and this is historical, right? We're talking, we're kind of organizing this through the history of different theories of perception. And not only is this, you know, information that's important to know, I really kind of want you to get the bigger picture here, which is how theories of psychology, or theories of perception in this case, kind of compete against each other and kind of flow into each other because of the different types of considerations, many of which have to do with data that's collected and emerging technologies. Oh, somebody asked, a participant has asked, yes, thank you. I'm so sorry. I thought that did it automatically. Here comes the transcript. All right, that is strange. Hello, transcript. Anyway, yes, we will continue with this discussion as we talk about the Gestalt theory a little bit more, and then go into another theory. Again, the sort of thing I'm after here is for you to understand how theories are evaluated and how theories are distinguished. And so that is something that you will be tested on your first exam. Now, I should say that this is probably pretty clear to you at this point, but this is a heavily conceptual course. This is not something that you'll be able to pass the first exam just by memorizing. You really need to understand these concepts. And what I've done today for our practice questions is I've chosen some questions that really tap into your understanding of concepts rather than any sort of memorization. And that is a different type of studying for a lot of you, I realize. And I'm going to give you a little clue now, even though we are some time before our exam, away from our exam. And that is, when you study, you should understand the concepts well enough to be able to explain them to somebody else. So after today, since we'll be finishing up with the Gestalt approach, you should be able to say, maybe explain to your friends, explain to your family, how the Gestalt approach kind of took over from a structuralist account. You know, what sort of a phenomena occurred, what led Wertheimer to consider this Gestalt approach based on the sort of observations he was making. And if you can explain it to somebody so that they can understand it, that means you understand it. You might know about these studies in psychology of learning that show that if you're studying for the purpose of teaching versus studying for the purpose of taking a test, you actually do better on an exam by studying for being able to explain it to somebody else. So, you know, the study was something like 2 groups of subjects were taught material, and one group was told, you've got to explain this now to a group of 10 people in a few minutes. So please learn this well enough so you can. The other group said you're going to be taking a test in 10 minutes. And then both groups took a test. And the teaching group didn't have to actually teach. But because they prepared to teach, they actually did better on the exam than those that prepared to take a test. And that's because the level of understanding one needs in order to teach, in order to explain to somebody else, is actually deeper and more flexible than the level of learning just for taking a test. And so it's that, for that reason, I really suggest that you do try to explain the material to somebody else. Maybe find somebody in the class that you can share a Zoom meeting with, and take turns trying to explain the material to each other. But you don't even need to do that. Just study real hard, make sure you understand things, write down your own notes, and then try to explain things to your siblings. And if they understand it, and you feel they understand it, and you can answer questions about it, that sort of thing, at least as far as the notes go, then you're in great shape. You're in better shape than if you just try to memorize. So studying for the purpose of explaining is a deeper understanding than studying for the purpose of taking a test. Okay, you'll see as we go along today and do our practice questions that is going to be a really useful tool for you to do well in the class. All right, so let's go ahead then and start continue our lecture on Gestalt psychology for today. And yeah, let's remember where we left off. And this is, in my mind, really cool stuff. So one way of discussing this slide was the notion that remember that box flow chart we used to describe the Gestalt approach? We said that in the critical box that distinguished it from structuralism, there were laws of organization that the brain, the perceiver, automatically applied to the input. And that was how the perceptual process worked according to this approach. And then it was the psychologist's job to understand that, of course, what those organizational principles were, and we talked about some of those. However, I put the word innate there, and I said it was innate laws of organization, but when I first mentioned it, I said, let's keep our eye on that word. It might mean something a little bit different here. And when we think about innate versus learned, we think about, well, you're born with this skill, you're born with this process or something like that. Like the brain is given this. Well, the Gestaltists did think this, but they didn't think it was like information given to the brain. They just thought, well, the brain, is something that is made up of material, made up of a kind of dynamics that have the same properties as magnetic fields or electrical fields, or even sand, if you want to talk about, the equilibrium process that happens when the tide comes in and kind of knocks things down. So one of the, kind of general processes of fields is this movement towards simplicity, the movement towards equilibrium. And that's something that happens with, monster magnets and paper clips. I know some of you flicked up a monster magnet. You knew that was my favorite toy, just to give you a sense of what it was like when I was growing up. But, paper clips kind of resettling, electrical fields resettling, sand resettling, all are kind of participating in kind of the field dynamics that occurs. And the Gestaltists said there's no reason we can't think of the brain in the same way, that rather than, kind of the more kind of common understanding of the brain is kind of neurons communicating with each other. We're kind of thinking more on a macroscopic, a kind of more global level about what the brain does. And what they're saying is the brain is like an electrical field. In this case, it's electrical chemical field, but it has the same tendencies to reach equilibrium states. So in comes a stimulus, and the, kind of the dynamics, the activity of the brain has to reconfigure itself and settle on an equilibrium state. And that equilibrium state is a stable state, right? Like, the sand being kind of pushed down with the tide, and the paper clips kind of reorganizing themselves with the magnet coming in. The brain also kind of moves towards simplicity. And that movement towards equilibrium or simplicity, stability in the brain, carries with it the perceptual experience. And that's what this isomorphism principle means, that there's a isomorphism, that there's a kind of matching, a kind of similarity that occurs in the brain state and the perceptual state. Okay, in comes a stimulus. The brain kind of moves towards its simplest configuration, which in this case is, the configuration that represents a triangle. And that, along with it, brings the perceptual state, the experience state. Oh, this is a triangle. Yeah, I do see the notch knocked out, but yeah, it's a triangle with the notch knocked out. And so that's what this means here. And what's, I think, really cool about this is a very different take on how psychology is working, how the brain is working. And they really kind of felt this was very far reaching. That, rather than thinking of, our experience, our mental states, our perceptual experiences as being something very different from, what we look at in biology and chemistry and physics, we can say that those perceptual experiences are following the same principles we see in biology and chemistry and physics, right? The brain and our perceptual experience along with the brain follows the processes of field theory. Okay, and that's kind of a provocative way of thinking about it, right? And that's coming back now to this intersection of biology and physics. We're kind of, the Gestaltists are trying to apply general physical principles of field theory to the biology, the neurophysiology of the brain. And that's kind of a radical perspective in some ways. And it's also their means to explain why the laws of organization all seem to move towards simplicity, all seem to, this kind of overarching law of prognons that the organization moves towards simplicity works. It works by the brain also moving towards simplicity because it's just part of the universe kind of moving towards simplicity. Kind of a provocative way of discussing this. And this is the kind of notion of psychology and natural law, trying to apply natural law to psychological principles, which at the time was very radical and I think still kind of provocative. So going back to the question, do the Gestaltists explain perceptual organization by assuming the brain is born with the knowledge of how to organize? That's not really what they're thinking. They're thinking, yeah, the brain is something that has these, kind of dynamics from the start. Right? We're born with a brain that has those dynamics, but it's not like knowledge the brain has, right? It's just, part of the physics of the universe, which is why I have all these silly figures here. When you talk about why the planets revolve around the sun, right? You talk about gravitational and centripetal and all that sort of stuff, all those forces. You don't talk about the planets having the knowledge of how to revolve around the sun, right? That's not a question of it. The planets develop by having the, important knowledge, having the kind of understanding of how to revolve around the sun. That's like, that's a kind of absurd way of thinking about it. And the Gestaltists are saying, yeah, that's kind of how we're thinking about the brain too. We're not born with knowledge. We're born with a brain that's part of a universe that allows it to be shaped by the same principles of field theory. Now, I see there's a hand raised. We will get to that in a second. I want to go through a little bit more in the Gestalt, and then I'll answer your questions. But hopefully you're getting that, and we're being recorded, and you can go back. I know some of these terms are new, and some of the ideas are new, but it's important stuff for you to know because this is, again, more far-reaching than perceptual psychology. This is a way of thinking of psychology in general. Which is important regardless of the type of psychology you're interested in. Anyway, okay, so we're talking 1940s, 1930s, 40s, around then. where it was really very much the predominant theory of perception, if not the mind in general, the brain in general. However, criticisms, like for all these theories, did emerge. And we should talk a little bit about these. These are all going to be criticisms now of the Gestalt approach. The first criticism had to do with the methodology that the Gestaltists were using. So remember, there were criticisms of the methodology of the structuralists. Just to remind you, people were concerned that asking subjects to kind of introspect on their sensory experience was not really very representative of the sort of thing people do when they perceive. And there were other issues with that too, in terms of how replicable these sorts of things were. But now with the Gestalt approach, here's a criticism, and it's not a dissimilar criticism. The first criticism is of the methods they used. And let me remind you the methods, then we'll give you the term. Wertheimer would have people sit, behind his screen when he was trying to demonstrate that apparent motion phi phenomena thing, and ask people what they perceived. It was a very open-ended sort of task. They'd say, oh, I see, two bars moving in opposite directions. I see two disks moving in opposite directions, or moving very slowly. Now it's moving too slowly for me to actually see it as motion. And now it actually looks like all those sort of things. They were very open-ended sort of tasks. Subjects could say what they wanted. And that was a concern to people. They thought, well, we do appreciate the Gestaltists trying to make this more of a science, but just by asking subjects, kind of, again, to introspect, not to introspect to the depth of the structuralist, right, but to kind of report their kind of perceptual experience out loud could be a problem. And so that's what's meant here by phenomenological observation. That's a fancy pants way of saying that people were asked to describe what their perceptual experience was in some detail. Okay, phenomenological. They're describing their phenomenology. They're describing what their current experience is. That's all that means. And again, it's not quite as as detailed as the structuralists. They're not having to say, oh, I see a red disc when they're seeing an apple, right? They are asking a little bit more about the perceptual experience, but by leaving it so open-ended, I see a disc moving back and forth, I see bars, all that sort of stuff. It became hard to kind of reproduce the same descriptions from one subject to the next, or from one time to the next. So by asking more open-ended questions of what the subject was experiencing perceptually right now in some detail, these phenomenological observations by the subjects, people had concerns about that sort of method. Okay. More than that, though, because you could imagine coming up with other methods maybe that were a little bit more refined, and the Gestaltists did think about that, but we'll leave that for one of the criticisms. More difficult, I think, though, was the kind of concepts the Gestaltists were using. And I think you'll have a feeling for this, and maybe even had a feeling for this as I was describing the approach a little bit, that these laws that are so important. Oh, hey, there we go. That actually is moving today. Okay, I have no idea why. On some days it doesn't, some days it does. I'm probably not seeing great where you are, but that's okay. The Gestalt laws, they're vague, right? So what does it mean? I mean, what does good continuation mean? What does closure mean? And yes, we have intuitions and we can kind of define them. You'll be able to define them on when you see the explanation on a test. But let's think about more precisely what they mean. When you say that these figures are perceived here as a triangle, a square, and a kitty cat silhouette, okay? Why? Well, because the mind, maybe the brain and the mind, tend to close figures. Well, what does that mean, close figures? I mean, there's, it's intuitive, right? You can say, oh, I'm closing up this, I'm closing up that. But we need to be more precise than that, I think, that what determines the very specific aspects that are closed, for example, or how could you describe mathematically how something is closed? That's just one example. I mean, what does it mean for things to, elements in the image to be continuous? It's kind of vague, right? We have intuitions that a smooth kind of sine wave looking line is continuous, and kind of jutting around and breaking up an image like that is less continuous. But again, it has to be more than intuition, right? If it's a law, we have to be very precise about how exactly this thing, what makes something precisely continuous and what makes something precisely discontinuous. We've got to be, if it's a law, like a law of nature, we got to be very precise about those sort of things. The same thing is true of similarity. We have intuitions that, yellow squares are more similar to each other than blue squares, which is why we see the cross in that similarity example. But what exactly makes them similar? How similar do they need to be? What if they were different shades of yellow or something like that? We've got to be very precise if these are laws. So you might have had maybe an intuition about this as we were going on, that it's unclear. I mean, we have a feel for what's meant by these laws of similarity and closure and proximity and all that stuff. But we have to, if they're real laws of nature, like law of gravity and everything, we have to be very, very precise about what counts as similarity, what counts as proximity, what counts as closure. The Gestaltists did a little bit of that, but they didn't emphasize that enough, probably. Okay, so that was something else. Now, this next one's related, but it's gonna be a kind of tricky term. Let me discuss it first. So how do they describe, why are these laws of organization true? And remember, we said there was an overarching law, the law of prognons, right? That said that, well, all these laws are true, all these laws of organization, right? Similarity, closure, proximity, and all 140 other ones that we didn't discuss. They're true because organization, perceptual organization, moves towards simplicity. Okay. Well, what does that mean exactly? Move towards simplicity. Again, we're kind of left open-ended here. How do you define simplicity, right? You can say that, well, it goes towards simplicity because of what's going on in the brain. Say, that's not good enough. How do we define simplicity, right? So by bringing in an explanation that kind of is as open-ended as the thing you're trying to explain, okay, we perceive things in the simplest way because of the law of prognons. What's the law of prognons? We perceive things in the simplest way. It's kind of a circular explanation, isn't it? Another way of saying that explanation, that law of prognons, is a kind of not a sufficient. Instead, it's a circular circular explanation. Is this term? Oh, there goes our sphere again. The problems become postulates. So what do I mean by that? That the explanations that are being proposed are really just restatements of the problem. The explanations that are being proposed are kind of restatements of the problem. And the law of prognons is a really kind of prime example of this issue, right? So why do we perceive things in their simplest configuration? Well, the law of prognons dictates it. That's why. There's your explanation. Okay, what's the law of prognons say? The law of prognons says we perceive things in their simplest configuration. See what I did? Again, I took the question and then made it a statement that I was then going to use to explain the question. And that's a real problem. It's a problem here, right? It's a problem for the Gestalt psychologists. The Gestalt psychologists were smart. They had responses to these, but we won't talk about it in this class. But it was an issue. I mean, people said, you can't just keep on saying the perceptual process moves towards simplicity, and that's why we perceive things in their simplest configuration. That's, circular explanations. It's not sufficient. Okay. I bring this up here not only because it's a interesting, important criticism of the Gestalt approach, but it is a criticism of things in psychology often. This is going to go now beyond our little perception class. Rosenblum's little perception class is again going to get a little bit more general. We have to be very careful in psychology not to use restatements of a phenomenon, okay, as an explanation. Okay, that's what I think. I want you to be very careful that for all your fancy pants psychology classes, is this explanation that's proposed more than just a restatement of the phenomenon? Okay, so let's go back to this law of prognance. Why do we perceive things in the simplest configuration? Well, the law of prognance suggests that. Okay, the law of prognance is that we perceive things in the simplest configuration. Okay, that's not a sufficient explanation. I don't think anyone's satisfied with that explanation. Let's move on now and talk about something outside the Gestalt approach. Let's talk about memory. Why do we remember our first grade teacher? Well, because that information is in our memory system. Okay, we have it in our memory. That's why we remember our first grade teacher. All right, what's our memory system? What's our memory? Well, that's where we keep all the things we remember. You see, even that, it can be an unsatisfying sort of explanation, can't it? Right? Why do we, kind of always, try to make the best of our situation or think the best of our situation, even if it's a tough situation we're personally in? Well, dissonance reduction. That's why you do it. What's dissonance reduction? Well, we try to, it's more than this, of course, but we try to make the best of, we try to think the best, we try to, reduce the dissonance that is unpleasant for us, so we think the best of our situation. Okay. What I'm trying to do here is show you that there are instances in psychology where a construct as a description of the phenomena you're trying to explain is used as an explanation. It's a big issue. It's a big issue for psychology, and it's something we have to keep our eye on throughout this class. And hopefully, as you go through your other classes, think, is this one of these situations where, the phenomenon we're trying to describe now becomes the explanation itself? We don't want to do that. That's not sufficient. We have to go further than that. Okay. I know that's a lot. And this notion here that problem becomes the postulus is just saying that we have this problem we're trying to explain, this phenomenon we're trying to explain of the Gestalt psychologists, that we perceive things in their configuration, and then to explain it we say, oh, it's the law of prognance. It's because we perceive things in their simplest configuration. It's just another way of restating the phenomenon. We have to be very careful of not doing that in all of psychology. Okay. But the Gestaltists might say something, okay, yes, we have to be more precise, but we also can say something about what's going on, what the basis of that law of prognance is, and we just learned this, right? It's the brain, right? The brain moves in its, towards its simplest configuration. However, there was some tests of this. So can we, in fact, think of the brain as an electrical chemical field? Is it a sufficient way of explaining perceptual phenomena? And there was actually, as I said, an experiment that was tested about this, which suggested that explanation may not work, that neurophysiological explanation. So that's what's meant here by it's neurophysiologically untenable. It's not supported by some data here. The neurophysiological perspective of the Gestaltist is not supported by this observation that was made around that time. And it's this, they used an animal here. I think they used cats, and the cats are anesthetized and all that. They're perfectly comfortable. But what they did is they taught the cat to respond when it perceived, one of these Gestaltist sort of figures here. And then they said, okay, well, we now know it is showing this kind of organizational principle, and possibly it's its brain kind of reaching equilibrium. But now let's mess with the electrical dynamics of what's going on in the brain. So what they did is put small pieces of foil, I guess, some sort of electrically, kind of dispersing or distorting foil into parts of the visual brain of the cat, thinking, okay, we're going to really distort, we're really going to mess with the field properties and see if that messes with the perceptual experience of the cat as much as we can understand it. And based on that study, they found, no, it didn't. You can put foil into the visual areas of the cat's brain, which absolutely would change the electrical dynamics, the kind of equilibrium process of the dynamics of the brain there. And the cat still responded in the exact same way. Okay. So messing with the field dynamics of the brain doesn't seem to mess with the perceptual experience as much as we understand that. Now, I should mention that I think things are about the brain and field theory are more complicated. Remember, we're talking about electrical chemical fields and all that. But at that point, it was important criticism, right? Saying this, at least with its kind of most literal understanding of how the field properties of the brain kind of bring along the perceptual properties that are experienced, this seems like it's not going to work, right? We mess with the field properties of the brain, we put foil into the brain, and we also should mess with the perceptual experience, but it didn't seem to for the cat. The cat still, as far as we understand it, pressed its little bar and was still perceiving these figures in the same way as they did before the foil was placed into their brain. Okay, so those are criticisms with the Gestalt's approach. But I should say that other things kind of led the Gestalt approach, at least for visual perception, to be less popular at the time, about 1940s, 1950s. And those things had to do not with criticisms, direct criticisms as such, but instead kind of emerging evidence, neurophysiological evidence, and technologies that actually were in some ways more supportive by our old friend, the structuralist theory. Okay, so I'll talk about these just very briefly now, and then we'll talk about these issues in more detail in just a second. But it was this. First of all, it was around this time, and you probably know about this from other classes, that Hubel and Wiesel, these two physician biologists, found evidence for cells in the monkey's visual brain that seemed to respond to things like the features that Wundt was so interested in finding, right? The feature detectors, these atomisms that Wundt was so interested in kind of using as the building blocks of perception. Hubel and Wiesel find that maybe there are cells that are sensitive to just these sorts of atomisms that Wundt was proposing, right? So you remember this story probably from your intro classes or 110 if you've taken it, that little recordings that were taken from individual cells in the back of the monkey's brain showed that there was a cell that was receptive when the monkey was shown a horizontal bar, and another cell that was receptive, that was active when the monkey was shown a diagonal bar, and another cell that was responsive when the monkey was shown a vertical bar. And those are exactly the sort of things that Wundt would have predicted, right? Like those features are critical, right? Remember the Gestaltists said, these features are really kind of interchangeable. The pieces are interchangeable. And Wundt's saying, no, the pieces are critical. And here now we have evidence that there are cells that are sensitive to those features, sensitive to these atomisms, as Wundt liked to call them. So there's this evidence in the 1950s for neurophysiological atomisms or feature detectors. Okay, that was one of the reasons I think that Gestalt really started falling out of favor at the time, along with the criticism that this turned out to be really important. And the other thing is, the computer revolution started then. And there's, I'm feeling nostalgic looking at that computer. That is a computer that I used when I was first a graduate student. In my lab, this is how computers looked. And these computers, which took up gigantic rooms, and had to be cooled from all this kind of fancy, ventilation that was underneath the floor, and it had to be programmed with punch cards, little cardboard punch cards. It did a lot less than your iPhone does right now. It was, this is how we used to do things, though. And we had to, in my lab, we were, analyzing speech sounds and stuff. But this is, these are the computers up through the 70s and even early 80s. This is what they look like. I had to learn, my first programming course was on punch cards. I know you don't care too much, but I felt nostalgic looking at that. In the 1950s, the computer revolution was starting to show that you can get a machine based on very, very simple principles, right? You know how computers work, the codes of ones and zeros, codes of on-off switches, all this sort of stuff. You can get a computer to do very sophisticated processing based on small pieces working together. And again, that's closer to structuralism in a lot of ways than it is a Gestalt approach. Again, the emphasis here being on the pieces, on the small atomisms, rather than the organization, that the atomisms, the small pieces count, and kind of, the way the pieces are lined up can support very, very sophisticated processing. So, the Gestaltists were going strong, and they offered some really cool ideas and really kind of pointed out some important criticisms of structuralism, that, maybe the pieces are interchangeable, and all of a sudden, the evidence for the neurophysiological feature detectors come out, the computer revolution comes out, say, maybe we need to, kind of look back to see what Wundt was saying and see if maybe there is some evidence there that we can now build into a revised structuralism that's more sophisticated and more based on now what we understand as computational processing. Okay, and we will talk about that next approach in just a second, but I think this would be a good time to take a little break, answer your questions, and do a practice question. Okay, let's take a look here. Good morning, everyone. Nancy says, imagine we only saw lines, and outlines. I'm not sure exactly what that's referring to in the lecture, Nancy. If you'd like to speak up, you can. If I answered your question, that's fine. Jenna, we remember our first grade teacher because they left a positive, negative impact, so they took up a piece of our space in our long-term memory. Absolutely. That is absolutely true. But what is long-term memory? Is that, in fact, an explanation? Yes, you're providing a much more nuanced explanation of why we remember them specifically, but why we remember anything is often explained by the concept, by the construct of memory, where memory is, in fact, the kind of storage house that allows us to remember things. And again, I'm being kind of simplistic here. You can get much more sophisticated about what memory is and maybe talk about the neurophysiological basis of memory and all that stuff. But at that level, we just have to be comfortable knowing that we are doing more, hopefully, than just, kind of restating what the phenomenon is, the phenomenon of remembering, and then saying, okay, we now have a mechanism that supports the phenomenon of remembering without getting much deeper into how that works. So we just have to be careful. It's kind of like a homunculus problem. We just don't want to, kind of keep on pushing the explanation back further and further and say we don't want to push the phenomenon that we're trying to understand deeper and deeper and say those phenomena are an explanation just by saying, oh, we have some sort of process that allows us to perform this phenomenon. Okay, yep, you're making good points though. Is this the type of approach or reasonably applicable to perception? Yeah, absolutely. So my concerns about the problems becoming postulates, the phenomenon becoming the explanation, is absolutely an issue for theories of perception. We have to be very careful not to do that. But I'm saying it's a problem for psychology in general. And I think probably, and philosophers will probably agree with this, it's more of a problem for psychology than it is the other sciences, because when we talk about mental constructs explaining different sorts of phenomena, very often those mental constructs are not thoroughly understood or explained well enough to be much more than a redescription of the phenomena that we're trying to understand. Okay, good questions, all of them. I don't see any hands up, so, but if something else comes up, that's fine. But let's go ahead and do our practice question, and I'd be happy to answer other questions after that. All right. Yes, this is going to be on the field theory. Okay. Ooh, this is a tricky one. I chose this one on purpose. So this is about field theory. Generally, okay. You know the context we discussed it in, but I just then went over it again, so you should have this fresh in your mind. Which of the following can be described by field theory? Okay, which of the following can just be described by field theory? A, magnetism. Can you describe field theory in the context of magnetism? Structures in sand. Can you use field theory to describe what happens with sand? The Gestalt's perspective on the brain. Okay, does field theory potentially apply there? Or D, all of the above? And given we just discussed this, it should be pretty straightforward. I'll give you about 45 seconds to answer this one. All right, you're doing pretty well here. Give me another few seconds. Okay. So most of you got this right, 75% of you, which is good. You know, you can go back and always look at the slide if you are confused, but the correct answer is D. So it's all the above. Magnetism, absolutely. I mean, think about my monster magnet and the paper clips. We are talking field theory by, using one one of the magnets in my monster magnet, or both. Things are reconfiguring, and it's absolutely appropriate in that context. And I think it was the original context where people were discussing field theory dynamics to describe what was going on with the reconfiguration of the the kind of particles, in this case being the paper clips. Structures in sand, yes, we talked about that in the context of equilibrium, that the tide comes in and knocks the sandcastle down into its most stable state, which would be, the sand flat on the ground. And then, of course, this is the whole reason we talked about this is the Gestalt's perspective on the brain. So all three of those answers are correct. The correct answer to mark on a test would be D, all of the above. And go ahead and take a snapshot if you haven't yet. And there you go, free questions. You know what's going to happen, I realize, because I'm going to take a little bit longer to go through this material for your test, you're going to have a lot of test questions. I think you're probably going to have almost a quarter of your test questions having been given to you because of our practice questions. So, hey, lucky you. Okay, terrific. Looks like there's another question under chat. Maimuna asks, so the computer revolution is supposed to show us that even if you move those small pieces in the computer around, it can work. Okay, very, very good question. The components and where they are located are much more important for what we're going to see is this kind of new computational approach to perception than they are the Gestalt approach. but there is going to be, it's not going to be as strict as structuralism. Okay, you'll see what I mean. We haven't started going through the computational approach yet, but you're going to see the computational approach, because of its kind of there's going to be a little bit more flexibility in the computational approach that's going to allow for, you know, some things to be a little bit less strict than the structuralist approaches, you'll see, but not as, certainly not as flexible as what the Gestaltists thought was going on. Okay, so let's start talking about that structure of the computational approach. So we'll drop that, go into this, and come back here and share our screen. There we are. Okay. Computational approach. Okay, so yes, a way to think about this is kind of a kind of updated, you know, we're still talking about the 1950s here, but you'll see this approach is in some important ways still with us. But it is an updated version of structuralism, but with much more detail of how things are working, and less emphasis on kind of the association between the features and stuff like that. We're going to get very kind of sophisticated about how features are put together here. So it is its own approach, certainly. But you'll see it certainly was influenced by the ideas of structuralism and this evidence that had come out recently that seemed more consistent with structuralism than the Gestalt approach. The thing about the computational approach is it is kind of the predominant approach in some ways that you probably have discussed in other classes when you've been discussing explanations of different sorts of phenomena. Sorry. This approach is sometimes known as constructivism or information processing, which can just be generally referred to as processing models or processing theories of how the mind works, which is a term I'm sure you've heard in other classes, right? You know, you talk about how we process information, how the brain and along with the brain, the mind processes information, whether it's information about our siblings, about our relationships, about our learning strategies in classes. When you talk about the brain, the mind processing, you are essentially using something like a computational approach. There you know, subtle differences between them, but what we're going to be discussing with regard to the computational approach is going to be generally relevant to every theory you've talked about in all your other psychology classes that referred to processing. Okay, so yes, we're talking about a theory that kind of emerged in the 1950s, but it is a theory that still is in many ways influential today. When it first came out, it was called artificial intelligence theory too. And it's kind of used a little differently now, I think, the term artificial intelligence. Back then, it was just generally meant to, I guess, argue that we can understand the mind of a person or an animal by understanding the processes of machines, by artificial intelligence. That's what this meant. We can understand the mind, we can understand the processes of the mind by understanding complex machines such as computers. That's what the artificial part means. And the intelligence part just means generally, it's used to discuss general mental process. Okay, that's the term, how the term was used originally. Okay, so let's go ahead and talk about a general feature. And the idea is this, and I think you'd agree with this, right? So when you think about, let's all think about our first grade teacher. You guys remember your first grade teacher? I do, Mrs. Becker. And I have good memories of her. I think I had probably more dynamic teachers in elementary school, but I have good memories of her. And I think about her and I can picture her face. What I'm probably dealing with here, it would seem, is a representation of Mrs. Becker, a representation of your first grade teacher as you think of her, right? And not just an image of her. It's, you know, like, you the sort of assignments that she might have given us, or the classroom. I mean, a ton of things that we are representing about her, about the class, about first grade, in our minds. So, and that would be true even if, and hopefully many of your first grade teachers are still with us. Mine aren't, certainly, but if Mrs. Becker walked in here, right, I would perceive Mrs. Becker, give her a hug, say, how are you? Thank you for being a good teacher, all that sort of stuff. But what I'm really relating to, and it should sound familiar, is again, a representation of Mrs. Becker, even if she's here, right? And what I mean by that is something we've discussed before, right? That my mind is not in touch directly with the world. It's in touch with, how the body is being affected by the stimuli in the world. Remember this idea of the doctrine of corporeal ideas. We're only in touch with how the body is stimulated, not with the things in the world. And then the doctrine of specific nerve energies was related to that. But the thing you can think about right now is our friend Keanu Reeves, right? Who you also can have a representation of, because he's saying, let's remember the Matrix, right? We have no way of knowing whether we are actually interacting with a real world or a representation of the real world that's artificial. And that's true, right? I mean, that what we are manipulating in our minds is not really Keanu Reeves, is not really Mrs. Becker, is not really Rosenblum, but a representation of all those things, right? And so one way of thinking about this computational approach is by understanding that the emphasis is going to be on how those representations are manipulated by the mind and brain, right? How is our representation of Keanu Reeves when that led us to think about the Matrix? When you probably, made that connection without me saying it, right? When I said Keanu, you thought of the Matrix. Maybe you conjured up that image I had on the slide of, that Keanu having a plug in the back of his brain, right? You were led to think about the Matrix. How are the representations of Keanu, of the plug in the back of his brain, of the movie The Matrix, of the concept that we aren't in touch with reality, only a representation of reality? How did those representations work together, go from one place to the next to the next? And what this approach is going to say is it involves manipulations of representations. All of our experience involves manipulation of representations. And we're going to get a little bit more precise about what we mean about manipulations here. We're going to say that those are computations. So this approach is going to emphasize understanding how representations are manipulated, or another way of saying that is just how computations are made on representations. That's just another way of saying the kind of precise manipulation of representations. Okay, so let's make this really simple and bring it back to perception, fundamentals of perception now. There's our Ponzo illusion, right, which I did a bad job at drawing, but did find a nice example of it in the textbook, where this line up here, horizontal lines, appears longer than this one below, even though, if you measured them with a ruler, you'd find out they were the same. Why is that the case? Well, things come into play here besides just the length of these bars as they're represented in the brain, starting with the back of the eye, right? Remember, I had you jump inside your brain for a second and take out your little homunculus ruler and first measure the lines on the back of the eye and take a note and say, yeah, okay, I now have a representation of those two lines and they're the same length, but there's other things there that I'm gonna see there, and these are also representations, right? That these train tracks are telling us that there's probably implied distance here in this image, right? That this area of the image is further away than this one because of the kind of converging lines, that linear perspective as we discussed it, right? So not only do we know that these are the same length, now we believe that A is in fact further than B. And so now we have representations of all these things in the mind, and we're manipulating them to get to the solution, because we know the size of something should be based on not just the image, that size that's coming in, but also something about the distance. And there's cues for distance in the image, which allows us to arrive to, in this case, the incorrect, but the sensible conclusion that A is in fact longer than B, based on what's available to us. But what's important here is that, remember, we call this an inference. This inference process is really involving the manipulation of the representations of all these things that are coming in. Okay, going from one stage to the next is nothing more than kind of manipulating representations, right? Or, to be a little fancier about it, because we're going to be talking about computations, we're just kind of making computations on these representations that are going to allow us to collect the representations and kind of evaluate how we should make a conclusion. So collecting and kind of putting them in the right order, and seeing how one conclusion leads to the other, is nothing more than making computations on representations. That's what's meant by that. That's all. It's a fancy phrase. Yes, it is a fancy phrase. Computations are made on representations, but you absolutely understand this. It's just, what's in our mind here is representations of things in the world. Many of them not great. Many of them need to be enhanced, right? And when we go through the process of using those representations, we're making computations on them. And the computational approach will try to understand the nature of those computations. Okay, that's where we're going with this. We'll come back to that in a second, but we're going to arm ourselves with some other concepts here that I think are going to be important for us to understand this approach. Oh, no, this is good. Okay, good. I didn't have this on my notes. I have this on the slide, though. Good. This is just, kind of what I've been implying here. Right here, this unconscious inference process, right? We're going to go deep into it with the computational approach. And because it's in here, we can talk about how representations are manipulated, how computations are kind of ordering these representations in a way that can lead us to make an inference about the world. And yes, our memory is going to come into play here too, but the memory is giving us representations of what might be out there, and allowing us to interpret those representations. And somehow we're going to dive into this box here and figure out exactly how the representations are ordered. Okay, representations of the bars, representations of the distance, all that sort of stuff to arrive at the percept. So this is, in a way, a nice a kind of flow diagram for the computational approach. Okay, also for the structuralists, but we're going to get very much deeper into this as we go through. Okay, we'll come back to that so you'll understand a little bit more. But before we do, I want to go to somebody who's kind of considered very, very important in this computational approach, and somebody you may have heard of, Alan Turing. So there he is. There was a movie about Turing's life. Oh God, when did this come out? 10 years ago? So you're probably pretty young. Called The Imitation Game. When did that come out? It's a good movie. It's really, it stars Benedict Cumberbatch. I'm just laughing because I every once in a while, one of my friends will send me a kind of reinterpretation of his name. They're very funny, but I won't get into that. But he's a great actor, and he plays Alan Turing. And the part of Alan Turing's life they portray is how he built a machine that enabled England to decipher the German code during World War II. And he's a fascinating character, kind of tragic character. He, besides being an absolute genius, creative genius, he was homosexual, and at the time that was not accepted. And he, they did, terrible, awful. They put him in prison for being homosexual. They gave him, chemicals, to, essentially suppress his libido and all this stuff. It was just awful, and he ended up committing suicide. But he has kind of offered so much, not only to engineering and logic, fields of engineering and logic, but also, as it turns out, psychology, because he thought very deeply about how we might be able to think of the mind as a machine. And then by going back and looking at how machines work, complex machines we're talking about, of course, we can understand the mind. Okay, so this is an idea that we'll be discussing called the Turing machine, because he kind of provided the basis for understanding this sort of thing. And it was a paper he wrote in 1936. Okay, there it is. So it was certainly really before the computer revolution. He was kind of anticipating the computer revolution, where he said that one can imagine a machine that is based completely on on-off states or on-off switches, right? So it could be a mechanical machine where you have switches that are on and off, like little light switches that are in a kind of groups, strings of on-off states, or the way he imagined it was a reel-to-reel tape recorder, which they had then, and marked magnetically on the tape, magnetic tape, were either charge or no charge, or one magnetic state versus another magnetic state. It really didn't make too much of a difference as long is just in one of two states. So a switch is on or off. There is either a magnetic, state that's on the magnetic tape. I'm kind of making this up, or it's off. It can be other sorts of devices that can be have strings of on and off states. And you might know this is how a computer works. A computer is a binary, works on a binary code that's just on-off states, but it's the strings of these codes, the on-off states. A or B would be another example, right? Zeros and ones are often how computers are discussed. But it can either be an A or B, these little configurations, and the string, the pattern of A, B, B, A, B, A, B, B, A, okay, when strung together, can be a tremendously powerful device. And that's what Alan Turing was showing us, right? By stringing together on-off states, you could, in fact, provide a machine with its own instructions. Okay, so this little code here, A, B, B, A, B, A, B, B, A, could mean that the tape machine, when reading that patterns of A and B's, should now forward the tape 2 feet and read what's there, read the code that's there. And there'd be a new code there, BBBA, BBAAA, something like that. And that code would say, okay, forward 1 foot of tape and then record something, record a string of 3 A's and a B or something like that, okay? So he was able to show mathematically, conceptually, that you can actually get a machine like this to perform some pretty sophisticated sorts of processes. Much more sophisticated than just fast forwarding tape and rewinding tape and reading code and writing code. Based on those sorts of actions, you could get it to solve problems, mathematical problems, okay? And this is what a Turing machine is it's a machine that's based on a simple binary code, strings of A's and B's, strings of zeros and ones, on-off states, and it can allow it to kind of control itself to ultimately perform some very complex processes. Okay, a couple of things I want to say about this. Beyond that, it's based on a binary code. It is an automatic machine in that it is kind of controlling itself, right? Yes, there needs to be somebody to kind of initialize the original strings of A's and B's and how they're kind of contingent on each other. But after a while, the thing goes on its own, right? That's what your computer is doing when you ask it to, look on the internet. You kind of give it a command, and then it does a whole bunch of things on its own, including controlling itself, so it can display, a web page for you and all that sort of stuff. And it's doing it based on this binary code. It's just gotten to be very, very sophisticated and very, very efficient. And Turing anticipated that. So, it's just going to be an issue of engineering. But yes, we can get machines to do amazingly complex things based on the code. It's automatic in the sense, the term automatic just here means that it's automatic in the sense that it kind of controls itself. It works on its own after it starts going. And another thing that is important about this is that the machine doesn't care what these strings of A's and B's, what these strings of zeros and ones represent. Okay, it's blind to that essentially. It's just a code, and the code could represent anything at all. And when we talk about something being a code that can represent a number of different items, a number of different things out in the world, if you want to talk about it that way, it's formal. That's all this means. It's maybe, you're used to formal as referring to maybe your senior prom. It was a formal, right? You had to wear a pink tux. You guys didn't wear a pink tux. Okay, I wore a pink tux to my prom because it was really in color, right? In fact, isn't that, I'm wearing a pink shirt today because I assume it's still in? I don't know. But anyway, that's how we used to think of it. That's how we usually think of formal, right? Here it means something a little bit different. Here it means that it's a formal process is one that is just a code where the code can represent many, many, many different things. The same code can represent many, many different things. And you probably know that's how your computer works. It's central processing unit where a lot of, much of this 0 and 1 code stuff goes on, of course, is able to represent so many things in the world. Anything that your web page is telling you, right? The infinite type of information is all being processed by the same strings of A's and B's, zeros and ones, on off states in your computer, right? Okay, so for example, mathematical systems are perfect examples of formal systems, mathematical systems. And so what does that mean? Well, here's a mathematical equation. And I usually, I think there might be about 125 of you actually. And say I have 250 M&Ms, green M&Ms, right? And I want to know how many M&Ms each of you should get. This time they'll have to be remote M&Ms, but if you were in class, we could give you how many M&Ms each. If they're 250 I have in my bag, and there are 125 of you. Well, math tells me that 250 divided by 125 is 2. Everybody gets 2 M&Ms. Don't eat them all at once, okay? But we also know that little mathematical system there, that little formal expression of 250 divided by 125 can represent many things, right? Let's not talk about M&Ms now. Let's say I didn't have 250 M&Ms. I had 250 adorable little chihuahuas with sweaters. Okay, and you can't see, actually in the building behind me, not the Leaning Tower, but the one next to it, I have 250 sweater wearing chihuahuas for you that I'd be happy to give you if you can come out here to Italy. Okay, and I would know if the whole class made it to Italy, I would know how many chihuahuas each of you get. You get 2 each, because the same mathematical equation, the same formal equation there can apply to green M&Ms and chihuahuas and sweaters, right? It's flexible. It can be anything. It can refer to anything. And it's an important component of the Turing machine that can be applied again and again, that the heart of how this machine works, the strings of zeros and ones, those 0 and 1s can represent anything that it wants to, in a way, right? So a Turing machine, this kind of conceptual basis for a computer, is binary, it's automatic, it can work itself, and it's formal in that the thing it's representing really doesn't matter to it at all. So we can say it's an automatic formal system. Cool. Oh, it has, yeah, that's what I want to say. It has no substance, no meaning. It's an automatic formal system. There we go. Okay, so hopefully you understand that. It's going to prove important because we're going to kind of have to deal with this philosophically later, because we're going to now try to see if we can not only understand computers like this, but understand people like this. Can we consider ourselves Turing machines? Okay, that's what we're going to talk about on the next slide. Well, let's just think about this conceptually. And I think probably because of TV and movies, the great, science fiction things, there's always this issue of like, well, can a computer, can a robot that's very sophisticated really think? And you are going to have such fun talking about this tomorrow in your discussion sections. I told the TAs to talk about whatever movies, whatever shows, whatever concepts they want to talk about with regard to this. And we all kind of come to these sorts of questions about whether computers can really think, or whether, if they can't, how are we different? But what I'd like to do now is talk about just the possibility that we can understand things like perception as computations, right? Computations made on representations that can be modeled, that can be understood with something like a Turing machine. So let's first talk about perception. And I think you see where we're going, right? That yes, a Turing machine can use those zeros and ones to represent things like linear perspective, to represent things like the length of those two horizontal lines. So yeah, in principle, that inference process can be processed by a Turing machine. You can get a computer, certainly, to kind of fall prey to the Ponzo illusion by having it represent these different things and then going through whatever manipulations that it can go through in its kind of Turing way. So yeah, you can model many perceptual problems, it would seem, many perceptual processes, more exactly, on something like a Turing machine. Cool. Well, what else can we do with a Turing machine? Well, Turing kind of envisioned this, as I said, by thinking of a magnetic tape, because that was kind of the machine that he was dealing with at the time. He also thought of it, by the way, if you see the movie, he thought about this in the mechanics of the machine he built to decipher the code. But in principle, he knew that any machine that can support a binary code can be considered one of these devices that can do this sophisticated processing. So what I mean here by substrate is just, what's the material of the Turing machine? Does it have to be a magnetic tape? And he knows it doesn't, right? That's what he thought of it initially, but he knows that any machine, any type of substrate, and I'm using substrate here just to talk about, lots of different types of material that can be considered machine-like. Any type of substrate that instantiates, that supports a binary system, can be considered this sophisticated processing machine, this Turing machine. Okay, so he talked about it as magnetic tape based. Yep, you can divide the little pieces of magnetic tape on the string as either having a magnetic on state or magnetic off state or whatever. Of course, that silicon-based computers, which is how our modern computers work, silicon switches are on and off. They're in 0 or 1 states. That's absolutely instantiating a binary system, and possibly our own systems, carbon-based. Oh, why do I have? Well, I think when I first put a slide up a few years ago, there was some issue about the breadth of her acting. There was this meme going around showing how she emoted and how her face looked with different emotions versus how Emma Watson showed different emotions, where her face was always the same and Emma's was different. So I was kind of suggesting that she had a computer-like style of acting, but no, I actually think she's a better actress now. But the important part is she, like Emma, like you and me, are made up of neurons that can be considered, at least on some models, as being in on or off states, right? You've gone through this, the kind of the all or none theory of neurons. Either they fire, they don't fire, kind of this trigger mechanism, right? Action potential, maybe you remember that term. If you don't, it's no problem, but you probably heard this along the way that at least according to how we understand some neurons, at least, they're either firing or they're not firing, right? They either have enough energy, kind of energy from the previous cells to kind of get to the axon and then fire to the next cell, or they don't. So at least on some understanding of neurons, we can consider those as on-off devices, meaning that the nervous system can be considered a binary system, possibly. Okay, things have changed a little bit since the 50s, but I think many of us learned this. Action potential really kind of is an on or off state, and in that way we can consider neurons and the nervous system as supporting, instantiating a binary system. So the material of the Turing machine, of this sophisticated processor, can be magnetic, it can be silicon, it can be carbon-based. I have one other example here. It's just a tangent. For those of you that are interested, if you ever go to the Boston Computer Museum, which is fun, it's a lot more fun than it sounds, there is a Tinker toy, which I don't know if you know what this is, the toy I grew up with, this and Monster Magnets, which is just wooden rods and spools. Somebody made a Tinker toy computer that can play tic-tac-toe as well as a human can, just to show that anything that is instantiating, anything that supports a binary system, on-off switches, can be a sophisticated processing device, leading to Turing and other people at the time to think of this, that human perception can be understood by how computers process information. Human perception, and possibly psychological states overall, can be understood by understanding how computers process information. Okay, this is what the original idea of artificial intelligence was about. That if we understand how a computer performs something, some sort of mental process, and you can kind of do that. You can do the Ponzo illusion at the very least. Then we can understand something about how the human brain works. All right, we will come back to that next class, but let's take our final break here for questions, and I'll give you a question. So the computer revolution is supposed to show something. Yeah, thanks, that helps a lot. Such a good movie. Jenna, are you talking about the Imitation Game? Yeah, it came out in 2014. Thank you for that. Yeah, so it wasn't that long ago. Okay, no study guides. Sorry, still no study guide because you got it on your slides, folks. Okay, anyway, all right, let's do our question then, since we're just running out of time here. I'll do it quickly, and you get a free question. Hooray. And this one absolutely has to do with the Turing machine, and we just went through it, so you should have no problem with it. One important aspect of the Turing machine principle is that perception can occur without representations. B, perceptual organization occurs spontaneously. Is that a Turing machine principle or a principle from another theory, maybe? C, any rule-based process can be modeled as an automatic formal system. Is that a Turing idea or not? And D, perception cannot be modeled on computers. Well, is that true? What did you just hear? Can perception be modeled on computers according to this Turing machine principle? It's a hard one. And I hate to have to do this, but I'm going to have to give you the question now. We will talk about it now, and I will also talk about it at the beginning of this class because it's important. So let's go ahead and do it now. Do your best. I know this is tough. Read carefully. We will do it now, and I will come back to this question at the beginning of next class, I promise. But let's get it in now since we have a minute. You're doing great. Nice. Good. Okay. I should end here. Sorry to give you less time this time, but it's almost 10:50. You did great. I'm really impressed. I really am. So, yeah, the correct answer is C. Okay, we are absolutely talking about representations here with the Turing system. That's what this is all about. Perceptual organization occurs, spontaneously, is part of the Gestalt approach, not the Turing system. And any rule-based process can be modeled as an automatic formal system. That is absolutely true, which we will talk about a little bit more next class. And we just heard that perception can be modeled on computers based on this principle. So D is incorrect. So the correct answer is C. Take a picture. I will come back to this and talk a little bit about it beginning of next class. Okay, have fun tomorrow in discussion section, and I will see you on Thursday.